Mühlbauer. I'm from Germany, the University of Applied Science. Our colleague from Waterloo was saying you're from a techie area. I'm also from a techie area. This area of Germany, it's very central. It's 20 minutes south of Frankfurt Airport, a hub that some of you may have gone through already. We're surrounded by big bangs and all the airport technology. We cooperate with them. So another techie standing here. My background is, well, I'm in the computer science department, so I'm a computer scientist. But when I was a student, I also studied linguistics. I'm a double major. Did that back in the United States. My background's in California, Berkeley. But then it pulled me back to Germany eventually. Okay, so today, and when I was invited to come here, I was, like you, I was thinking about, what am I going to talk about? And I thought I'd like to present a project that I've worked on for the past 3 years, together with students and also with industry. It's a cooperative project, which is a project which is a little bit atypical to the projects that we run in our department. In various senses, and I'll talk about that. So one of the key words in the topic of the talk is barriers. And when I talk about barriers and barrier-free routes, what I'm talking about is things like this: narrow passages, pictures that, these were taken in Germany, but they can be anywhere on the planet. It could be in the US, it could be anywhere really. Stairs, surface conditions, and curbstones, barriers that we find everywhere. We don't only find them outdoors, we find them indoors. So that's what the project is about, is taking care of handling barriers that we find outdoors and indoors, and enabling people who do have impacts on their mobility, help them, aid them in their routing. So when we look at the user group, or when we did look at the user group, when we started the project initially, we were looking at who are we talking about when we're looking at mobility impaired users. And most of the time you'll be thinking of people in wheelchairs, but that's not the only people who are mobility impaired. We have many more people who have problems walking or getting around, people who have walkers, young mothers with strollers. You don't need to be 50 plus to be mobility impaired. You can be well younger than 30. Crutches, canes, impairments, which can be also only temporary. So lots of reasons for being mobility impaired. So it's quite a big user group. And we wanted to also get a feeling for the numbers. And because we are located in Germany, we first looked at numbers in Germany and Europe. And these are numbers that were provided by what's called the statistical, it's a governmental institution collecting statistics. And the numbers that we got for the European Union, having a little bit more than 500 million people, so it's somewhat comparable to the US population. We're looking at about 1.86% of the population in the EU that is sitting in wheelchairs. The numbers that were given to us in Germany, they were, they weren't really contradictory, but they were different in the sense that some sources gave us 1.46%, others gave us 1.95%. The reason why these numbers varied was because of the definition of how they defined being handicapped or mobility impaired. And the other reason was for including the temporary need for mobility assistance. So that's why these two numbers, they're a little bit far apart. But when you look at the numbers across Europe and Germany, they're quite similar. So we're looking at approximately 1.9% of the population that is sitting in wheelchairs. But when you look at those, and that's why I initially gave you the pictures of, you know, people who are mobility impaired. It's not only the wheelchair users, it's a whole lot of other people. The number of mobility impaired people in Germany, it's higher, definitely higher. So it's around, but it's between 5 and 6%. And this number is pretty much the same because we're in the US here. I was looking up numbers in the US, and it compares to numbers that the US Census Bureau in 2014 gave for the United States. So we're looking at about 5%, between 5 and 6% of the population that is mobility impaired, and that's quite a large number. So having given that, and actually for the US, the numbers are very, very detailed. The numbers in the US that you find, they're much more detailed than the numbers I was able to find for Europe and especially Germany. In the US, it's divided up into all the different states. And you do find in an annual report of 2014 of the Institute of Disability from the University of New Hampshire, numbers for all states in the United States on ambulatory disability, which is defined as people who are either in wheelchairs, they're paralyzed, or they've lost one or two legs, and or they're permanently impaired. And the numbers across the United States differs between Hawaii, with having the lowest number of mobility impaired people, being 3.3%, and West Virginia being quite high, above 10%. So these are all numbers that we can't ignore. You know, it's a large amount of the population that is impaired, mobility impaired. And what's that?
What happened to California and
Just really light.
really light?
It's very light. It's hard to see here. That's actually the Pacific Coast down here. So
Yeah.
California is in this range between 3.3 and 4.4%.
Radical difference between that and New Mexico.
I cannot give you the reason why California has lower numbers. I just took the numbers from this source that I gave you.
All these rich islands going to Florida, I would think Florida would be high.
Yeah, Florida definitely would be high.
Isn't that odd?
Yeah, I was wondering about that too.
In West Virginia?
Well, this is a very, very detailed report, and I mean, for those who, you know, most of you are from the United States, you may want to look up the reasons why this is so. I just found it very interesting because the numbers you get for the US and the reasons, they're much, much more detailed than what I was able to find for Europe. So it was quite interesting to see that.
Where did that come from, CDC or?
It's from, this is the source, the Institute of Disability from the University of New Hampshire. They have a rehabilitation, research, and training center, and you can actually find it looking it up under this URL here. I took it right from there. So anyway, what I'm saying here is we're not looking at a super low percentage of population. We're looking at a high number of people who do have or who are mobility impaired. So what I want to talk to you about today is the motivation of why I decided to run a project for this user group. And actually, I already gave you couple of criteria why I did it. Then I want to talk about present navigation tools and how we use them and enhance them and change them. And then I want to talk about the application that we have developed called Wheel Scout, talking a little bit about the implementation, and also want to give you a look into the future. So like I said, some of the motivational factors I already told you, it's a large number or a big group of people that we want to develop a tool for. I wanted, my personal interest was also to do something for the people around me, not just always enhancing programs for industry, but I really wanted to do something for people around me. Then I'm not working in industry. I'm a professor at university, so I also wanted to open my students' mind for our responsibility as computer scientists in society. That's something computer scientists sometimes forget. Computer scientists are usually very techy. You know, they're very happy sitting in a dark room, ideally closed windows, closed doors, and then programming. So ethics and philosophy a lot of times are unknown topics to them. So this is something that I wanted to bring to them. So I think responsibility is something that's very, very important, especially when you're a computer scientist. And then also, technically, it's a very, very interesting topic because mobility in mobile computing is something very interesting. Exact positioning and routing, both outdoors and indoors, is extremely interesting because it's technically different. Developing a user-friendly GUI is also something that's very interesting for a computer scientist. And then my topic includes via voice control. So we do have a speech recognition front end. So we have included speech recognition, which is also very interesting. And there are a lot of features that come from artificial intelligence that we have included in the project, in our app. So just from that side, from the techie side, it's also very interesting. So when we look at present navigation tools, these are just a few that, you know them all. TomTom, Garmin, Google, OpenStreetMap, you name them. And some of you may have, like myself, flown into Orlando, you get a rental car, and then you try to make your way from the airport to SeaWorld, to this hotel. And when you type in the route into OpenStreetMap, OpenStreetMap will show you something like this. It will give you Orlando Airport, and actually it routes you somehow south and then back up here to the hotel. And typically in OpenStreetMap, what you can choose from is either going by car, walking, or riding your bike. So you have 3 different means of transportation. And then depending on the means of transportation, it will show you different routes. If you type this into Google Maps, you get a slightly different route. Again, Orlando Airport takes you to I think this is called Toll Road 528 or something. And it takes you right into the hotel here. And again, we have different means of transportation, which are shown up here. I'm enlarging them. So what we have here is not only car, bicycle, and pedestrian, but we can take public transportation, buses. Oh, no, actually, this is car, sorry. This is car. This is public transportation, train. You can also walk. You can ride a bike from the airport. I'm not exactly sure how you want to do it by plane. Maybe a little helicopter. But then also, what's not included is another option, which is our mobility impaired people. We have done quite some research on existing navigational tools, not just the big ones, also small ones. We have found one little prototype of a system that attempted to compute routings for mobility impaired people, but nothing that's on the large scale and out on the market. So we took this lack and defined our project around this. And we said, okay, we're going to develop a tool, the Wheel Scout app. And I want to introduce you to the features of our app. Now, the prominent features that distinguish our tool from existing navigational system is that our tool computes an intelligent detour in case there are barriers found along the shortest possible route. So if you want to go for a walk from, let's say here, the hotel across the road, and there's a staircase, it will take that into consideration and compute a detour. The barriers that are found along the route will be marked and will be explained. So you can always decide to check on what type of barrier the system did detect along the route. Everybody can define a personal profile. We also found during our research that there is no default wheelchair user. Everybody is very unique. We found wheelchair users that were able to climb upstairs. You know, in some people, they wouldn't even be able to go up a little curbstone that high. So it's very, very different. We can include barriers into our maps, both permanent as well as temporary barriers. You know, sometimes we have fallen trees or, you know, whatnot, which is not a permanent barrier, but so we also take those into consideration. There's a high degree of interactivity that I'll talk to you about in a second. And then the latest item that we added is our voice control. We found that quite a large number of, especially our wheelchair people, they also had mobility impairments in all their limbs, not just the legs, but also in their hands. So a lot of them were asking for speech recognition and voice control, so we've added that. In terms of the intelligent computation of detour, the first feature that I mentioned, we're using the traffic light metaphor. So when there are unpassable barriers, meaning, you know, large staircases, etc., along the route will be marked as red. If there are barriers detected along the route which may be barriers for some users and not for others, we'll mark them as yellow. And if it's a barrier-free route, it will be marked as green. So this map actually shows all three different types of routes, navigating from a starting point to a goal. And you can see here, there's a barrier-free route detected. The shortest route would have been this one, but there are barriers along this route. And this route, the yellow one, will contain certain barriers, which may be barriers for some people and not for others. This is another example. This is an example going from my campus, this is our campus, to the train station. The shortest way from the starting point, marked here as S, would be across campus, but unfortunately there are staircases. So people are routed around it. A detour is shown from the start to the end. And this is all computed on the basis of the personal profile, which defines, in this case, not being able to climb or go downstairs. We have developed certain icons which will, at a first glance, already show you what type of barrier we're talking about. We have defined, at this point, 8 different types of barriers, which are the ramps, the narrow passages, stairs, tilts, construction sites. Temporary, whenever a barrier is temporary, it's marked with a little red clock. For indoors, the elevator, which may be out of service, and difficult surface conditions, like muddy underground or something like that. The next feature is the marking and explanation of barriers. So when you look at this route here, with the starting point being here and the goal being here, the shortest route would be this one. But it leads through a park, and there's a little curbstone here. So a detour is being computed, which is barrier-free. We see at first glance that along this route, there's this barrier. There are some other barriers in this area that's shown, but you know, they're not of interest for this route. So these are the 3 barriers that we see. The only one that's of interest is this one. And we can actually click on it and get information on this barrier. Because this is a curbstone, it's defined as just having one stair, and it's set 10 centimeters, which is about 4 inches high about. To get an idea of what it looks like, this is part of our user group. We constantly work with wheelchair users. This is the curbstone that's marked in the map. And actually, one of our users, he fell when he tried to climb it. the next feature is defining your own personal profile. We have to find defaults. Because some people, they say, okay, we don't want our own individual profile. It's okay if I'm a default user. So we've divided up into active, electric, and help-dependent wheelchair users, and have defined, like I said, a default. And this is the GUI, the graphical user interface, for these profiles. And you see the 3 defaults here. But you also have the individual ones. So when you click on this, what happens is another menu opens up where you can define, certain underground, certain surface conditions that you can handle or not handle, and what areas you can drive on, whether you can climb stairs, etc. And you can give that profile a name. In this case, I'm putting down Bettina, my first name. So, and then what happens when you submit that to the system, your own personal profile is included in the system, and from then on, only your personal features will be taken into consideration during the computation. Like I said initially, we can include permanent and temporary barriers. Very important, especially in heavy weather conditions. A lot of times we have situations like this, trees, fallen trees, puddles of water, snow, some debris, whatever, little potholes in the street. The default is for these to stay in the system for 2 days. If another user didn't confirm that this barrier is still there, it will disappear. Otherwise, we'll have an overload of barriers in our system. The way to include barriers is the users include them. Some of the barriers, we get them from OpenStreetMap. We're using the routing system, the routing computation that we use, the maps. They're from OpenStreetMap because they have an open interface, and we can pull their information into our computation. OpenStreetMap does have some barriers included, some stairs, but it's not extensive, and it also depends on where. Cities are better mapped than other areas, so we found that we definitely need to include more barriers, and we're letting our users do that. The way you do that is you click on this little plus, meaning you want to add a barrier, and then you get this other GUI, this other menu, including the type of barrier. You click on it, and then you add the features for the type of barrier. In this case, a narrow passage, and you've defined the width, and you can also comment on it. And once you've saved the changes, it gets added to a database, and from then on, it's available for all the computations. The routing always has a start and a starting point and a goal, like any other routing systems. We can also go via a position. So if you decide you want to stop at a bakery or something on the way, you can do that. The way the route looks like then is you have a starting point, you have a goal, and then you also have the position that you want to stop by. And in this case, the green route shows you this is barrier free. You want to stop here, you need to go back. And instead of taking the shortest route, which would be this one, it leads you around it. You can always get the information on the length of the route. You could click on the route, you get the information on how long, because that's a lot of times very important for our wheelchair users to decide, because they know how long a distance they can travel. So this is important information. And instead of only doing outdoors, we're doing indoors also. Okay, and indoors is quite a different story. Outdoors, we can use GPS coordinates, and we can use mapping, like I said, from OpenStreetMap. Indoors, quite a different story. We don't have GPS connection indoors. So what we need to do is we need to map our buildings. Because in a building we have lots of walls, we have doors, and we need to tell our system exactly where a person can move. So what we're doing is we're using fire evacuation plans because they're true to scale, and we use those and map those onto our buildings. And when we then, I'm going to skip this, when we then look for a route inside the building, in this case from here to here, it shows us where we can go and which is barrier-free. This also works from outdoors to indoors. In this case, we have an outdoor starting point. No, we have an indoor starting position, an outdoor goal. This is actually our computer science building, and there's a staircase here at the entrance. So what our system is doing is computing the detour on the barrier-free route. So indoors to outdoors, and this is just another example of outdoor to outdoor. And this is interesting because the shortest route is going through a building. And I mean, that's what we do all the time. If the shortest route goes through a building, you know, we walk through the building. You know, it's like if you want to go from the pool to the outside of this hotel, you go through the lobby. You don't go all the way around. So this is exactly what this map is showing. Thank you. And we can, like I said, we can combine outdoor and indoor. We can also do the routing across floors. We don't only have one-story buildings. We have buildings with different floors. So if you want to go from a position from outdoor on level 0, on level ground floor, and you want to go to a position that's on the second floor, a little marker comes up here that says you can change floors. So what this is doing, it's leading us into the building, to the elevator, going up onto the second floor, and then from the elevator, it leads us to the goal. So it takes indoor positions into consideration. The implementation, because I only have a minute left, like I said, outdoor, indoor is very different, but because outdoor we use the GPS coordinates, which are very exact. Indoors, GPS a lot of times doesn't work, so we use what's called Bluetooth transmitters, or so-called beacons, which can locate you. They can locate any phone. What's similar in both outdoor and indoor is what's called trilateration. So you always need, in outdoors, you need signals from at least 3 satellites that compute your position. So you have 3 satellites, and at the point where all the circles meet, that's your position. And that's pretty much how the beacons work as well. So trilateration is sort of the secret behind it. The speech recognition, just one word on that. What I initially said is we have a multi-modal interface. We can type in our goal and destination. We can touch on the screen, but we can also talk into it. So if, for example, we're asking the system to navigate from Darmstadt Hauptbahnhof, which is the main train station, to a city plaza, what happens is 2 things. For one thing, it shows us the map. It shows us the main train station to that city center. But it also shows us what has been recognized. So if you read this and you figure, oh, it wasn't recognized correctly, you can repeat it. And we can train the system. Actually, the recognition gets better when you train it. With any speech recognition systems, that's the case. And the steps of processing for that is that first the speech signal is transcribed to text. Then we can train the system, like I said. The good thing is that we're working on a limited corpus. You know, you're not asking the system to give you the weather forecast or something. So it's always something like, show me the way from to. So these prepositions are keywords for us that we look for. And then the verbs, they're always, you know, show me or navigate me to or something. So it's a limited corpus, which makes it easier for us to train the system. One last feature that we have included, in which is related to artificial intelligence, is when there are ambiguities. For example, if you don't tell the system if you only give it a street name but not a city, sometimes people do that. If you're within Orlando and you want to go to Main Street, you're saying, I want to go to Main Street. You're not saying Main Street, Orlando. Then what happens is the system is automatically looking for the street that's closest to your present GPS position, and that comes in first position, but it also gives you alternatives. So having said that, that's our app, that's our Wheel Scout app, and for those who are interested in seeing it, we can actually, we do have intranet here. I can, some other time later today or tomorrow, we can play around. And actually, the slides are available, and the URL that you can use to test the system is given. So feel free to test it, play around with it, and any comments, they're welcome. We're still in the development process, so any feedback is more than welcome. Thank you very much.